There are a lot of places that are like that.
Everybody
It's really maybe, it's actually,
not because they
want
want
to
to
make
pay
things
for it,
out.
because they don't study for JF.
That's right.
Alright, why don't we go ahead and get started?
Are you willing to be
Right, so we've got, we're very happy to have Akaxia Cruz here today. So Akaxia got her PhD at University of Washington under Tom Quinn, right? Yeah, not Matt McQuinn, but a different Quinn. And she's not far from us now at Princeton and CCA. So if you'd like to talk to her more, she'll be here this afternoon for a bit. And then of course you can talk more at CCA. Without further ado, Akaxia, tell us some cool simulations.
Okay. Yeah, so instead of talking about sort of long-range interacting dark matter and plasma physics, I'm going to talk about this other part of my research, which is using hydrodynamic simulations of galaxy formation. And I promise I will talk a little bit about dark matter in there as well. So I'm going to start with something that's very basic, and many of you know, but I don't know, I feel like I have to say this for some reason. So I'm showing the matter energy content in the universe, and we know that dark matter makes up most of the matter in the universe. This is us, this really small fraction of 5%. And cold dark matter, which is collisionless and cold, agrees really well with observations from large scales. So here I'm showing the matter power spectrum inferred from cosmological measurements ranging from the cosmic microwave background in green to the Lyman alpha forest in red. Now this red line is for a lambda CDM model, and you can see that it agrees very well on these large scales. We think that dark matter halos form from these overdensities, which you can see here in white. And once you put on gravity, you can see the production of these dark matter halos, these white sort of nodes here. And we think that galaxies form inside of these dark matter halos. So when you go to these small scales, there has been shown to be some tension between the cold dark matter prediction, which agrees very well with large scale observations, and what you see in particular in dwarf galaxies. And so an example of this is if you look at rotation curves. So here I'm showing rotation curve data from, and mostly what I was talking about is rotation curve data from Spark. So this is these very high resolution rotation curves from H alpha and H1. And so CDM predicts, so cold dark matter, if you have a cold dark matter only simulation, you can parameterize dark matter density by the mass of the halo. So for a fixed mass, which these systems are roughly the same fixed halo mass, or Vmax, you can see that NFW or CDM produces identical rotation curves. So that's this black with this gray shaded region, which corresponds to the scatter and mass concentration relationship. Okay, so this is in contrast to what we actually see observationally though. So here I'm showing a rotation curve that is more steeply rising in the central region than NFW, whereas this rotation curve is more slowly rising in the central region than NFW. And so this you might think of as typically corresponding to a core, if you think back to the old core cusp problem, but I'll go into that a little bit more in a second. So people have tried to quantify what is called the diversity of rotation curves problem by looking at the central velocity, the central velocity corresponding to this fiducial radius, which I have described here. This is to account for the mass scale, and then this fiducial velocity, which is always to try to probe this central velocity, corresponds to the circular velocity at this radius. So people have worked to quantify this diversity by looking at the central velocity versus the maximum velocity, maximum circular velocity. So again, this is the NFW prediction, this black line, this gray shaded region. The points are now colored by what's called this eta rot, so V fid by Vmax. So this is basically a proxy for how fast or slowly you rotate in the central region, where below approximately 0.65, you're rotating more slowly than NFW in the central region, and above, you're rotating more quickly. And this dashed line is 1 to 1. And so what you'll see is between approximately 50 and 100 kilometers per second, there's this large spread at a fixed V max, which is a proxy again for the halo mass. Okay, so that's the basic problem, this diversity of rotation curve problem.
It looks like you can just fit a line to all of them, right? If you go back, I mean, it's slightly steeper slope than the gray 1-to-1, right?
Mm-hmm.
You know, is that fit for something, or do you know what like that slope is, or?
I don't know what the slope is. I don't know if anybody has quantified that. That's a good point. Yeah, I don't know. I can't think of anybody that has directly quantified that. But yeah, either way, it's steeper than the NFW prediction. Okay, so
Can I ask? Sorry to interrupt again. Can I make you go back again? What are you? This is VFID over Vmax is the x-axis. What do you do in these cases, like actually most of them, where it doesn't look like the rotation, which is pretty typical for dwarfs, I guess, which is the rotation curve isn't converged yet.
yeah.
So I guess that makes it, I guess that if I make the Vmax bigger, it just makes this problem worse, right? So that's not really gonna solve your problem.
Sorry, let me think about it for a second. So that means you'll be lower here. You'll be further down.
Yeah, you'll move to the, so if we went further out in these rotation curves, these things would just move further to the right.
Yeah, I think so.
Okay,
And yeah,
So
so
it'd be worse.
I'll get back to this point.
okay.
Yeah, I'll get back to this point about the fact that the rotation curves are still rising in some of these objects, and how I'm trying to account for that in the simulations. Yeah. Okay, so there are generally two classes of solutions that people think about. Of course, these are dwarf galaxies, so there's galaxy formation. So one idea is, okay, well, what happens if I just add the galaxy formation? And here is an image where you see, the background dark matter filaments, and then you see these regions where you have this strong feedback. Previously, people have showed that this feedback can significantly alter the central regions of dark matter halos. So these effects can really matter. A second class of solutions is what happens if you just drop the collisionless case and you let the dark matter have some self-interactions. And in this talk, I'll mostly talk about hard scattering self-interactions. Okay, so I'm going to start just by thinking about the case of what happens in cold dark matter with baryons. And this is basically just what I said before. You see these, you see the cosmic web, the dark matter. If the video played, you will see that even though ordinary matter only makes up 5% of the matter energy content in the universe, you can still drive these really energetic outflows and rearrange central regions of dark matter density profiles. And so this goes back to this old sort of core versus cusp problem. And so just to sort of demonstrate this, so the old core cusp problem, which I think has mostly evolved into what we're now calling the diversity problem, is you have, again, from cold dark matter only predictions, you're predicting these very cuspy, centrally dense dark matter profiles from dark matter only. Whereas if you looked at observations, 20 years ago, from rotation curves of dwarfs, that's these colored lines, you'll see this more flat densities in the central region. And so what I'm showing here is from a simulation with cold dark matter and supernova feedback that can suppress these central regions. So you start with something that's very steep in the central region, you get these bursty outflows from supernova feedback, and then you can create these dark matter cores. So this is one potential solution that people think about. And to quantify this a little bit more, or to think about how this might translate into diversity, people have looked at this. So I have this cartoon just sort of explaining some of the language I was using before. So this is the dark matter density as a function of radius from the center. So this dashed blue line is what is often called a dark matter cusp. People often parameterize the central region just as a power law. So r to the negative alpha. Oh, sorry, I guess it should be r to the alpha since I used negative 0.5 here. A cusp typically corresponds to something around negative 1.5 or 1, whereas what the observations were showing from the old core cusp problem is closer to a slope of 0. But this actually depends on the mass of the system, what the central slope looks like. And so for Milky Way-like galaxies, here you have the baryons are really dominating the potential here, and so you can get slopes that are even steeper than this cold dark matter only prediction because the baryons are really dominating and driving the potential voltage even steeper.
So you mean that alpha is 1.5 or minus, because you already have a minus?
Yeah, I'm sorry. I'm sorry. So this should be
This should be a plus.
This should be a plus, yes.
Okay.
I'm sorry. And so you can see that here. So cold dark matter only predictions is these x's, and you can see that the cold dark matter only prediction is the slope of negative 1.5. Now this is for various, the colored regions are for various simulations. So different simulations use different prescriptions for what their galaxy formation looks like. But in general, they share a similar trend. And you see that there's this large spread, particularly like around these bright dwarfs, where this diversity of rotation curves is maximized. Now, due to the spread in this relationship of the slope, as well as the spread in the stellar mass-halo mass relationship, this could potentially translate into some rotation curves rising more slowly in the central region and some rising more quickly in the central region at a fixed halo mass. That's one potential solution in cold dark matter. Now the self-interacting dark matter case, there's sort of two different solutions, two broad classes of solutions if you just consider these hard scattering self-interactions. And so to explain that, I'm just going to talk firstly about sort of the evolution of a self-interacting dark matter halo. So there's sort of two phases. It's more complicated than this, but I'm just going to roughly talk about it in two phases. So you have this initial core phase, and then you have a core collapse phase. So here on the left, I'm showing dark matter density profile. On the right, I'm showing velocity dispersion. And velocity dispersion is a proxy for temperature. And when you allow the dark matter to self-interact, you basically have a way for the dark matter particles to now exchange energy that you didn't have in the cold dark matter case. So this is colored by look-back time. So this dark purple line is 10.2 years ago. This is the beginning. And you see that there's a hot outer halo, again, this is proxy for temperature, and a cool inner halo. Now these self-interactions are going to exchange energy and try to drive you into an isothermal distribution. So they want everything to be in equilibrium. And this translates into going from a chord profile to something that's more custom. So that's the core extension phase. Now there's the secondary phase that happens because you're in a virialized system. You end up with this negative peak capacity. So now what happens is energy starts to flow the opposite way. So you are losing heat in the central region, but you're heating up the system. And so the colors are wrong here, but the velocity dispersion should be going up, and this corresponds to this core collapse phase, similar to what you would see in globular clusters.
Again, sorry, I mean total amateur. So is this robust against the form of the self-interaction? What self-interaction do you have in mind?
I'll talk about that in a little bit.
Beg your pardon?
I'll talk about it in a couple of slides. I'll talk more about the self-interaction specifically that I'm going to consider.
Okay, but it's robust to the results.
It depends. I mean, so how fast or slow this happens depends on the strength of the interaction. So how fast or slow you get into this core collapse phase depends on how strong your cross-section is, as well as the mass of the system and the concentration of the system. Now these two are coupled, right? And so there's some scatter in this relationship between the mass and the concentration, but you should expect that you have a fixed, at a given mass, you have a fixed cross-section, and so then you also have a fixed mass. Then because of the scatter and the mass concentration relationship, in this scenario, you expect some of the halos to end up where you're in the core expansion phase, whereas others at that fixed halo mass are in this core collapse phase. So you'll also produce this spread in central density, right? Which could translate into this diversity. But I'll talk more about the specific cross-section in a little bit. Okay, so the second case, sorry. So the first case is what I just said. You don't need baryons at all. It's just purely you have a really large cross-section. You have some scattering and mass concentration relationship, which can produce this diversity. The second case is instead, I want the cross-section to be pretty small. So 3 centimeters squared per gram, such that all of these halos actually end up in this core, should end up in this core phase. And now what happens, the way that you produce diversity, is by what's happening with the observed baryons. So the points here and with the error bars is data from Spark again. And in this Wren paper in 2019, what they did was they assumed a cross-section of 3 centimeters squared per gram, and they fit these profiles based on this self-interacting dark matter model, where they change the amount of baryons that contribute to the potential. And what they showed was that, okay, so these more purpley curves, these are more high surface brightness objects. So in this case, the potential is dominated by the baryons, and so SIDM can't form more core. You get these more steeply rising objects because of the help of the baryons. Whereas these redder rotation curves, I'm sorry, this is not colorblind friendly, but these red curves, or these more slowly rising rotation curves, are low surface brightness galaxies. So in this case, dark matter dominates the potential, and you can produce a dark matter core from the self-interaction. So in this case, it strongly hinges on the fact that you're able to simultaneously produce high surface brightness objects as well as low surface brightness objects, which we do observe in the universe. Okay, so that's the 2 different sort of scenarios for self-interacting dark matter. So what I'm trying to do is I'm trying to probe all 3 of these models in this suite of simulations. So the first suite is this very high resolution suite of simulations with cold dark matter and baryons. A second suite is where I have baryons, but I'm going to just choose a low cross-section, and I'll tell you in a little bit what that cross-section looks like, where the host ends up in this core expansion phase. And the third case is where you have a very high cross-section, and you produce this core collapse phase in a Hubble time. So just to tell you sort of the status, I have roughly 40 of the CDM with baryons. I have about 20 of the core expansion in baryons, and then these ones is still sort of in a numerical convergence testing, but I have done some with baryons, and I'll show you some preliminary results from that.
Can you just go back a second? Sorry. So
this?
no, to the list of the numbers of simulations. Sorry. How do you do number 3 without including the effects in number 2? Right, like doesn't the presence of the baryons, like it always functions in this way, right?
Yeah, I mean, so I agree with you. I mean, I think that in the third case, you do always have to consider baryons. There are baryons in the real universe. That's how we're able to even see these things, right? It's through the luminous counterpart. So I agree with you. Typically when people talk about this third scenario in the literature, they are purely thinking about it in the case where you don't have the baryonic component. They're showing, oh, I can create this diversity even without the baryonic contribution. I can do this purely with self-interactions. Now, what the baryons are going to do to this, people have some sense of what it will do, right? By considering static potentials and then still doing things analytically. What we're really trying to do, or what I really want to do, is try to also see what happens, the back reaction of the baryons. What happens in the presence of this core collapse of the baryons? Do you get, steep potential wells where you produce lots of stars, you get starbursts, and then you sort of break this scenario? I don't know. Nobody really has, nobody really has done cosmological simulations here with baryons.
And so I understand, and just so because I'm interested because all of these things also, but in the number 2 case, it sort of allows you to do this even when the timescale for gravitothermal collapse is really long. Like, is that sort of where 2 is appropriate? Like, it's just too long for gravitothermal, but you can still do it.
Yeah, exactly.
Okay.
I mean, so eventually everything will gravitothermal collapse.
Yeah.
In this case, it's just that the gravitothermal collapse will happen after a Hubble time.
Right. Okay.
And so we just want to consider all 3 cases. This case is much easier than this case. This case is really numerically challenging. This case is easy in some sense.
Yeah.
Right. But even here in this regime, not a lot of people have really tried to explore with a large sample of simulation what happens when you have core expansion SIDM and then you include galaxy formation. Right. Even that there's still holes in our knowledge. Okay. So I'm just going to talk about a little bit what has previously been done in the cold dark matter case. So previous simulations of cold dark matter and baryons actually really struggle to produce this diversity, in spite of the fact that I showed you, there's this potential, solution. So here's again the observations in this upper left-hand panel, and now I'm showing you for various suites of simulations where they consider different types of star formation for the most part. So in this upper case, this is from the Apostle project, where the simulations have a star formation prescription such that you cannot produce dark matter cores. So even in this case, you wouldn't be able to solve the core cusp problem with these simulations. So you are only producing objects that are more steeply rising for the most part than NFW in this regime where diversity is maximized. In this evil case, you have a very high density threshold for star formation. So in this case, you get this really bursty feedback, and you only produce dark matter cores. So you're not producing any of these more steeply rising things, sort of at 100 kilometers per second, down to 50 kilometers per second. And then the third case is this Nihao project, which is actually the closest to the simulations that I'm going to present. And in this case, they're scanning a little bit larger mass range. And in this case, again, sort of below or at 100 kilometers per second, they're only producing dark matter cores. So they're not producing those more steeply rising objects. Okay, so I want to say one other thing about dwarf galaxies, which I think is important from an observational perspective and will play into this problem. And that is that if you look at observed dwarfs, they also have diversity if you look at their size, so their half-light radius, as a function of their stellar mass. And in particular, you should see at a given stellar mass, so at or below 10 to the 9 solar masses. This is spark. This is this late time galaxy prediction. So this is normal sized galaxies. So you should see objects that are more extended than normal sized galaxies, but you should also see compact galaxies at a given stellar mass. So this means that you should have some high surface brightness objects and some low surface brightness objects. That's what we observe. Okay. Again, previous simulations are really struggling to produce these really compact objects. So I'm showing Nihao in the squares. They're only really producing these very diffuse or extended objects. The same thing from this loopy project, as well as fire. So at or below 10 to the 9, kind of state-of-the-art simulations are really only producing more compact objects, more extended objects, and really struggling to produce compact objects. Okay, so now I'm going to talk about the CDM and baryons simulation suite. So I'll just tell you a little bit about the simulation suite. So the first set of simulations comes from this sort of sheet. So we do a zoom sheet several times. So we produce several different volumes. And this allows us to produce dozens of dwarfs down to ultra faints. And that's just basically what this is demonstrating, is that you can get down to very low surface densities in both gas and dark matter in these simulations. And I'll show the mass scale of those in a second. And we complement this suite that had already existed by these more massive zooms. And so this set of simulations was really designed to really try to target the regime between 50 and 100 kilometers per second, where diversity is maximized. And even if you just look at them, just at first glance, so this is mock UV ion images of these simulations. So the side lengths of each of these boxes is the same. And so you can see that we're already, at first glance, you can already see that we're producing objects that are very diverse in terms of their morphology. So we're producing both very extended objects, but we're also producing very compact objects in just cold dark matter with baryons. Okay, and then just so you have a sense of sort of the masses that I'm talking about, up here in the teal, this is this more massive set of dwarf simulations. And so the mass range that we picked to really focus on the diversity of rotation curves is between halo mass of 10 to the 10 and 10 to the 11. And then we sort of complement this with those dwarf volumes in the maroon squares. So we have halo masses down to close to 10 to the 9, and then up to a few times 10 to the 11. Okay, so I showed you this before. Sort of what other simulations are doing. This is assuming spherical symmetry. So you're just assuming sort of mass enclosed. In this paper by Isabel Santos, what she does is instead, she looks at what happens if instead I forego the spherical assumption. So instead of assuming that the circular velocity goes like the square root of the mass enclosed, over R, I instead actually calculate the potential, and then I calculate the circular velocity from the potential. Okay, so I'm just gonna focus on these left two panels. In the teal points are data, and these gold points are from the Nihal simulations. In the case where she uses spherical symmetry, she's again really at, sort of at or below 100 kilometers per second. She's really only producing these more slowly rising objects, and she's circled these gray observational points, which she is unable to produce, that are more steeply rising. Even if she goes into the case where she uses the potential instead of using spherical symmetry, which, like, if you have a disk and the disk is dominating the potential, you really shouldn't, have spherical symmetry. Even if she assumes a potential, she is still really only able to produce these more slowly rising rotation curves, and is still really struggling to produce these more steeply rising rotation curves simultaneously.
Can I ask a dumb question? You can't, in these simulations, just look at the velocity of the gas?
In some simulations, yes.
But not in Nihal.
Like, if you want to do a direct comparison, like if you want to do like mock H1 or something, right? To do like a realistic comparison with what you would see observationally. I don't think that in Nihal you can do that.
Okay.
In our simulations, we do have H1 information, and so we are going to use the H1 to try to do, sort of more mock observations in our simulations, and I'll show you that.
Is that a matter of resolution, though?
Yeah, it does depend on resolution
Okay.
and the way that
Right.
in your star formation prescription. Yeah. Okay. So this is exactly what I'm saying. So in this case, I am directly considering the H1. In so much as that, you were saying before, a lot of these rotation curves, when you look at them, they're still rising at their last point, right? Because they have limited H1. There's like some cutoff in H1, which corresponds to roughly 1 solar mass per parsec squared, right? So what I have done here is, in the simulations, I take the same cutoff. So I'm restricting my rotation curves to sort of agree with what is done observationally, where I don't necessarily always have the most, the highest velocity, because it's limited by the amount of H1 I have in my system, okay? So in the spherical symmetry case, I'm actually closer to what's happening in Apostle, in that so this is the NFW prediction, this is spark, this is the one-to-one line. I'm really only producing these more steeply rising objects. Now if I go to the case where I calculate the potential, and I use this H1, these H1 limited rotation curves, now I can produce, sort of, I said, I kept harping on, below 100 kilometers per second, down to sort of 50 kilometers per second. I'm able to produce simultaneously a steeply rising thing, as well as something that is more slowly rising than NFW, in this cold dark matter case with baryons, where I had this high resolution, I did this H1 limitation to my rotation curves, and I'm able to produce these objects, both slowly rising and more steeply rising than NFW. Okay.
Can I ask you about this? Sorry to keep interrupting, but is that saying, though, like the fact that the top one, oh, I see, both of these are limited. Both of these are limited.
Yeah, they're both limited.
Okay, fine. Okay, never mind. I have to think harder.
Yeah, okay. We can chat more.
Yeah.
Okay, so actually, in some ways, I'm more excited about this. And this is more like, less about dark matter, more about galaxy formation. But okay, so I said before, if you look at, 10 to the 9 stellar mass and below, these previous simulations are really only producing these diffuse objects. Now, if you look at my simulations, so this is also R1/2 versus stellar mass. This is the late time galaxy prediction with 1 sigma. This corresponds to sort of normal sized galaxies. Things above it are more diffuse or extended. Things below it are more compact. And the point of this is that not only am I able to produce these, sort of diffuse objects in this model, but I'm also able to produce these compact objects. And this is the first time anybody has been able to produce these more compact objects. So that tells us something about galaxy formation, aside from dark matter. But these two things are related, is what we're showing. And so in some sense, you do sort of have to be able to produce these more compact things. And we think to also be able to produce these more steeply rising objects. So this is again how fast or slow we rotate, again relative to NFW. This is the NFW prediction. This is more slowly rotating than NFW. This is the half-light radius. And then this is colored by the dark matter mass fraction. So these things you can see are more baryon dominated. They're more compact objects and they're more steeply rising. So I think these two things are tied together, at least in the cold dark matter case. Okay, so now I'm going to go to the case where I think about core expansion, SIDM.
Sorry, before you do that, what new physics have you included, or what causes your simulations to produce more compact galaxies?
Yeah, so I have a student at Princeton who is helping me think about this a little bit. So if you think about size of galaxies, people have thought a lot about what sets size in galaxies in more massive systems. Less so in dwarf galaxies, but what we're seeing is that it's an interplay sort of between what's happening at large scales as well as what's happening in terms of the galaxy formation. So roughly the picture that we think is happening is the more extended objects, or the more disky objects, they tend to be spun up by very tangential mergers. So there's some exchange of angular momentum between the host and some merging objects that can help you create the more extended objects. You can get that from other effects as well, but that's one effect we're seeing. In the secondary case, we're actually seeing, for the compact objects, we're seeing very radial mergers, where the gas just kind of centers at the center of the potential. And we think what's happening is it's a combination of the star formation. So in all the previous simulations, the way that people do star formation is they just sort of have thresholds for where they think the star formation should start to happen. So if it's significantly dense, then and significantly cold, then start forming stars here. Whereas we're trying to use a more observationally driven approach where we actually use molecular hydrogen cooling, so H2 cooling. And this allows the gas to actually cool more realistically, more in agreement with what you see observationally, and it cools a much colder, dense gas. Okay, so that's one thing. The gas has to get really cool and dense. The second piece is it does matter what's happening with the feedback. So I've done a couple of simulations that I'm not going to show here because I'm not going to show you, the skeletons in my closet. But I did a couple of simulations where I change what the feedback prescription looks like. So I keep the star formation the same, prescription the same. I change the feedback. I have the same initial conditions. So what's happening on the large scale structures is the same. And now if I crank up, if I make what's called this early supernova feedback, it's very bursty and it puffs up these very compact objects. So it changes them from being very compact to being more sort of diffuse. And that, so the model that I use for that is exactly consistent with Nihao. So I basically have just reproduced Nihao galaxies, and that will be, all the details of that will be in this paper that's to come. And we think something similar is happening if you go to, like a fire-like prescription of galaxy formation. They just have very strong feedback. They're puffing up their galaxies. Okay, so the self-interacting dark matter case. I want to be roughly in agreement with observations. So what I'm showing here is that, so we know at the high mass end, the self-interacting dark matter cross-section is constrained by shapes of clusters. So that's roughly to below a centimeter squared per gram at the high mass end or high velocity end. But this recent paper by Minosh Plingett shows that if you look at satellites of the Milky Way, so that's what I'm showing here, satellites of the Milky Way from Gaia, and in particular these ultra-faint dwarfs, these lines are cold dark matter prediction. So these ultra-faint dwarfs are very dense, such that either you have to have cold dark matter in these ultra-faint dwarfs where galaxy formation doesn't matter, you're not going to be able to produce cores because the baryons, you don't have enough energy from the baryons to actually produce cores here. So either you have to be CDM, or the cross-section has to be so high that you're producing core collapse in these ultra-faint dwarfs. That's basically sort of where we're pinned. So now we have a velocity-dependent cross-section. We need this velocity-dependent cross-section. And this paper by Camila Correa, she tries to quantify this by using this gravel thermal model. So again, she is describing the interactions just by this Yukawa potential. Instead of doing fully cosmological simulations, she's using the Scrabble thermal model. And from that, she is making some prediction for the shape of the cross-section in order to match these satellites of the Milky Way. So I will say that her model does consider tidal stripping, which will accelerate how fast or slow the core collapse happens. So that expression that I showed you before for the core collapse time will actually be accelerated if you have a surrounding tidal field. And so that will be important in a second. But a fact that she doesn't consider is ground pressure stripping. And so in some sense, this line that she has produced is sort of a lower bound at this mass scale, so between 10 and 100 kilometers per second. So this is sort of a lower bound on the shape of the cross-section in this velocity range. Okay, so now I'm going to show you the cross-section that I'm going to use for the remaining simulations. So again, this is the transfer cross-section per dark matter mass as a function of velocity. Now I'm showing the Correa prediction here. There's this extra factor that there's this parameter in the Scrabble thermal model in the heat conductivity, and so I'm showing where she's assuming two different cases. But this is roughly the cross section that Correa has predicted, and her predictions are sort of in between 10 and 100 kilometers per second. And so I have picked this purple cross section, which agrees with Correa's predictions in that mass range, and also agrees with the high mass end, so is below, roughly centimeters squared per gram at cluster scales. So this is sort of again a lower bound, and this is what I'm going to use for what I'm going to refer to as my core expansion CDM simulation. So that's the case where the baryons really matter. Now what I've done to show you sort of like where are you going to get core collapse. So what I've done is I said that the core collapse time depends on the mass and the concentration of the system as well as the cross section. So what I've done is I've done fits to my CDM simulations, and I know they're M200, and from my fits I calculate what C200 is, and then I say I want the collapse to happen within a Hubble time, and that allows me to back out what the cross section needs to be for each of these simulations, and that's these dotted points here where in a given line I've changed what the T collapse is between I think 9 gig years and 13 gig years. And this blue curve, I'm saying, is the velocity-dependent cross-section that I need to still agree with the large-scale structure, but to also produce core collapse in these systems. And again, I said Correa was a lower bound, so this cross-section is still viable.
Akaxia, just to check, so the sigma over m, right, you said it could have velocity dependence, and which is set by the mass of the galaxy, right? So is this an integrated, or what is this TC? Where does the velocity dependence come in for sigma?
Right. Sorry. So yeah, so you are integrating over the angles.
Right. Right. Sigma can have velocity dependence, right? Or are you just considering sigmas without velocity dependence?
No, this is velocity, right? This
Right.
is velocity dependent. I don't understand.
Oh, I guess maybe on this TC plot, TC function.
Yeah, I guess I'm assuming that this is like at a given time what the cross section is. But yeah, so there has been more I think this is generally done in the case where you do have a constant cross section. There is more sophisticated formalism for the case where people consider what this prediction looks like for the case where you do have a velocity dependence. I'm not showing that here. Okay, so the core expansion SID case. So I said, this was the prediction from Ren. These are fits that they've done to data, assuming a cross section of 3 centimeters squared per gram and a self-interacting dark matter. Okay. Now, if I look at my simulations, I produce the same thing. So here I'm looking at, I'm trying to match this as much as possible. So circular velocity is a function of radius from the center. I've limited my velocity range to the same velocity range as in this Ren paper, and I'm showing roughly the same behavior. So now I've colored this by surface density, which I show here in the colored line. So these objects up here, these blue things, are higher surface density, and these more red curves that are more slowly rising are lower surface density. So I'm producing, a similar thing as what I'm seeing in this front paper. I've just verified it from simulation. So I'm not doing a fit here, this is actually a prediction, whereas this is a fit. Okay, but if I go to the cold dark matter case and I include baryons, I get a similar behavior, right? So again, I said that the baryons really matter in what's happening here. There's some relationship between how fast or slow you rise in the center region with the surface density or the size of the galaxy. And sort of that's what we see observationally, we see this relationship. But I'm also able to produce this relationship if I just go to the cold dark matter and baryon case as well. So this is, higher surface brightness galaxy, it's more compact, something that's more extended, and lower surface brightness.
Wait, sorry, is this a different plot?
Yeah, this is a different plot. So I'll go back and forth between them, okay?
Okay,
Because they are,
yeah.
there is a subtle difference, okay? There is a subtle difference. Okay? This is now CDM with baryons. My point is that you're hinging on the baryons. This argument hinges on being able to simultaneously produce high surface brightness objects and low surface brightness objects, or extended and compact objects, right? Okay, so I'll go back. This is
I see.
SIDM core expansion with baryons. But this argument again hinges on me being able to produce realistic galaxies, right? Okay, so this is the core expansion.
All right, okay, so those are different curves.
Yeah, they're
I
different.
missed that.
They're different, and there's subtle difference in the shape.
Yeah.
Okay, so now I'm going to look more at a population level. I really have only targeted this high mass bin in my my SIDM core expansion simulations. I don't know. I'm thinking maybe I'll do some more down here. I don't know. I haven't decided. The circles are the CDM with baryons, and the plus is SIDM with baryons, and then the color is for the matching simulation. And so the point is, again, in this mass bin, between 70 and 100 kilometers per second, I'm producing compact things, and I'm producing more slowly rising things in both the CDM and the SIDM case, where you have these low cross sections and are in a core expansion case it's equal to. There are some subtle differences, so you just pointed out, like, go back and forth between them, you can see that the shapes are slightly different in the core expansion case versus the CDM case. And there is a slight shift. So again, this is a proxy for how fast or slow you rotate in the central region. There is a slight shift in the core expansion case, so that's this dash case, versus the solid case is the CDM plus baryons. So these things do tend to be a little bit more slowly rising in the SIDM core expansion case than in the CDM baryons case. Okay, so if you look at these rotation curves, you can tell that their shapes are slightly different. And that is mostly due to if you look at their density profiles. So here now I'm showing dark matter density as a function of radius from the center. And I'm just showing a collection of objects which I have a match in both the CDM and the SIDM case. The CDM is the solid line in all of the figures, and the SIDM is the dashed line. And what you can see is that the SIDM case, even though you are producing cores in the CDM case with the feedback, you're producing less centrally dense dark matter profiles in the SIDM case, and you're also producing more extended cores in the SIDM case compared to the SIDM plus baryons case. And that translates into these slight differences in the shapes of these rotation curves. Okay, so just to talk about this a little bit more, that difference. So here now what I'm showing is just two galaxies, where now I'm showing the central slope at 500 parsecs as a function of cosmic time. The teal line in each case is the CDM plus baryon run, and the orange line is SIDM only, and the SIDM plus baryons is the gray. And so the point is here is that the self-interactions are really dominating and helping you to set even lower central densities with larger dark matter cores in this model. Okay, so this is for a subset of the objects. Now if I look at a different, two different objects, something different happens. So again, central slope, cosmic time, CDM is always, is more steep with the baryons. But now in this case, the orange is again SIDM only, and the gray is if you add the baryons. So now what's happening is that the SIDM-only case is flatter in the center region than in the case where you add the baryons. So it seems like the baryons are having some effect here, some extra effect. So it seems like the baryons are maybe contracting these systems. Okay? So I want to look at this a little bit more in detail, and that's what I'm trying to do here. So now I'm looking at the half-light radius as a function of the core radius. Same markers styles as before, but now I'm coloring each point in terms of the dark matter mass fraction within a half-light radius. If you look at the cold dark matter prediction with baryons, this is sort of in one mass bin. What you see is that you're roughly producing a 1 kiloparsec core. These objects, I'm still not super sure about. Some objects, have had recent major mergers, so I'm still trying to think about these. But either way, there's a much steeper relationship. So this is a one-to-one line. There's a much steeper relationship. There is a relationship between the half-light radius and the core radius in the SIDM case. And so this is because, again, the argument that came from before, SIDM thermalizes the dark matter halo, and it really ties together the baryons and the dark matter. So these things, where you're more extended, the dark matter is dominating, right? And so the core can be really big, whereas in this case, the baryons are really dominating, and they're contracting the system. They're contracting the system. Okay, so now I'm in this case where I am able to produce diversity in sort of like, both cases, the SIDM plus, the SIDM plus baryon case and the CDM plus baryon case. Now, how do I disentangle these two things? Maybe not through diversity, I can produce nice diversity in both cases. So how do I disentangle them? Well, I said the cores were bigger, and I showed you just now, that the cores are bigger in the SIDM plus baryon cases, and I also showed you, previously, that the central densities are lower in the SIDM case. Now I'm going to show you a simulation that has, all of these simulations have intermediate mass black holes. So what I'm showing here is this is the formation of a galaxy. So the stars are pink. This white dot is a black hole. Here's another galaxy that's formed, and there's its black hole. It just merged with another galaxy. Now these two things are going to merge. You're going to see this production of stellar streams. This black hole sinks to the center of the potential, but it sort of wiggles around. But this black hole that just came in from the merger just oscillates around this central black hole. And if we just keep watching this until z equals 0, the question is, they're going to dance around each other. How long are they going to dance around each other? Are they going to merge? I don't know if I want to make you go watch the whole thing, but long story short is, the whole age of the universe, they just dance around each other and they never merge. And so one way that I'm thinking about trying to probe these differences, in light of, now I can produce diversity in CDM with CDM with baryons. I can also produce it if I have a low cross-section SIDM with baryons. One way that I'm trying to think about trying to probe this is by thinking about mergers, black hole mergers. The suppression of the central density, these larger cores, the dynamical friction time goes proportional to the background density. So that means that in the SIDM case, maybe you have longer dynamical friction times. So you have fewer intermediate mass black hole mergers, and maybe that will allow us to say something about trying to differentiate these two models. Okay. Now I'm just very briefly going to talk about the core collapse case. Okay, right. In some sense, this is motivated by this plot that is very busy, which I will try to walk you through. So this is again from the Santos paper. This is the observations, and then this is for those 3 different simulation suites that she considered in that paper. So these points are now colored by Vmax, which is again a proxy for the mass of the system. On the y-axis, she's again showing this eta rho parameter, so how fast or slow you rotate. These things above this gray line, which is the NFW prediction, more steeply rising than NFW. These things down here, more slowly rotating. Now the x-axis is the mass, the velocity in baryons at this fiducial radius, so the central radius, divided by the total velocity squared. So this is basically a proxy for the baryon mass fraction within this fiducial velocity. So just think GM over R, spherical symmetry. Okay, So I'm gonna start actually with these objects here, because I don't know, can help me get some intuition. You can see by this color bar that these things have pretty high Vmax, so they're pretty massive systems. These are like Milky Ways. And so in this case, it makes sense that they're, and you can also see that here. So they have high central baryon mass fractions. And so these things are more steeply rising because the baryons are dominating the potential. You're getting baryonic contraction. Okay, so these ones make sense. These ones are kind of weird in this picture, in this intuition, the spherical symmetry intuition. They have low central baryon mass fractions, but they're more steeply rising than NFW. And Sanchez basically shows that in any of these different models of star formation, I can't produce these objects. They're hard to produce. And so somebody who is an advocate for core collapse SIDM would say, oh, I can produce these things. I don't need baryons to produce them. I can make these really centrally dense objects that have low baryon mass fractions by invoking these very high cross sections and getting you into this core collapse regime within a Hubble time. Okay, but I can produce them in these CDM simulations, so you don't necessarily need this case, but I'm going to consider it anyways. Okay. So now I'm showing one simulation because these are very expensive. Basically, the time step is set by the central density. And so as you get into this regime where you have very high density, the time step becomes very small. And so that means that these simulations tend to be very expensive. So I picked the blue cross-section from before, such that I know that my simulation will collapse. Okay. So this is the central density. It's actually averaged within a kiloparsec as a function of cosmic time. And you basically see this picture that I said before. So it starts as being pretty dense. You go through this core expansion phase, which is obscured by, you have a bunch of major mergers in this gray band. So that's why this gray band is here. It's sort of obscured, which is this kind of effect is hard to probe in a gravel thermal collapse model, gravel thermal model. And then after this, actually after you get to sort of your maximal core, you get this core collapse, and you end up with something that is very dense in the central region, almost an order of magnitude more dense than the CDM plus baryon case. And just to show that this translates, roughly into a difference in VFit by Vmax. This is the CDM case. It's it's still above NFW, but it's not at the 1-to-1 line. Whereas this SIDM core collapse case does really make you produce these very steeply rising rotation curves. Okay. Now I'm going to answer your question about the baryons. Why would you ever consider this case where you don't have the baryon? So like I said, people are considering these types of models where they add the baryonic contribution to the potential by just assuming some static potential for the baryons. In this case, I'm doing fully cosmological simulation, so I can look at the back reaction of the baryons. And the point is, light blue is the dark matter only simulation. Now this purple line is if I include the baryons. And the point is that the baryons just speed up or accelerate the core collapse. So the core collapse happens faster if you include the baryons. What's happening with the star formation here is absolutely mind-boggling, and I still don't fully understand it. But this is sort of like a preliminary thing, just to show that even in this case, the baryons do matter, and they really speed things up. Okay, so dwarf galaxies exhibit diverse rotation curves. In this new set of simulations with CDM and various models of self-contracting dark matter, in core expansion SIDM, these low cross sections, if I sort of use these mock observational techniques, I can produce this diversity. I can also produce, for the first time, both compact and extended objects at a given stellar mass, which is important because we observe them. This core expansion SIDM produces similar diversity, but you can't rule it out, and so we're trying to think about other ways to try to disentangle the self-interactions from the baryons in this case. And these steeply rotation curves with low baryon mass fractions are motivate these core collapse SIDM, but you can produce them in CDM plus baryon. And And then I just want to acknowledge my awesome collaborators and the
Questions for Akaxia?
So, since you now have these simulations, can you then take the different scenarios and translate this into additional observations, like going to high redshift or looking at, field versus dense halo? What are the things that you can then look for to tell you whether these knobs are the correct ones to be turning?
Yeah, so now we are trying to think about different ways that you can probe these things with like an ensemble of objects. I am trying to think about some high redshift stuff, more with the black holes though, and at a different mass scale. I still personally think looking at the black hole mergers is an interesting potential way to explore this. Another thing that we're trying to look at is the shapes of the dark matter density profiles and compare that to observations, and see if there's some relationship between the shape of the dark matter versus the shape of the baryons. Yeah, I don't know. We have these simulations, so yeah, we're trying to think of other ways, other observables to try to pull these things apart.
Okay, again, amateur question. So you have dark matter, and then you're decorating it because you need to feel diversity.
Mm-hmm.
So there are two types of questions. Are diversities also emerging in other type of galaxies? That's question number one. And question number two, quantitatively, what percent are the decorations and what percent is the core assumption of, let's say, dark matter and then cold dark matter?
Okay, so the first question about do you see this diversity in other systems? You mostly see it, so I showed in that previous figure. You don't really see it at a high mass end because the baryons really start to dominate those systems, and you just mostly see very steeply rising rotation curves. You do see diversity sort of, mostly the diversity is sort of maximized for sort of classical and bright dwarfs. That's really where you're seeing this diversity in the properties is sort of classical bright dwarfs. Okay, so the second question. Ask me again. Second question.
Second question is, you have a core assumption, which is dark matter and cold dark matter.
Yeah.
And then you're decorating it by various things. What percentage of what you explain is from the core, and what role do the decorations play?
Okay, so by decorations you mean like different types of interactions and galaxy
Different
formation?
type of interactions, having the baryons play an important role. So what is important? Is it a 10% effect,
I see.
20, 1%?
I see. Yeah, I mean, I haven't quantified any of those things in particular, but you do see, by looking at other various models of galaxy formation that you can get very different looking, simulated galaxies. I would say that the simulations that we have that are sort of motivated by what we think are more realistic models of galaxy formation, that we are able to produce objects that do look realistic, more realistic than all of these other models where people are only producing more slowly rising things, only producing more steeply rising things. For the
Finish, sorry.
For the self interactions, you're also seeing effects from the self interactions, but I haven't explicitly quantified.
But like one of your first slides had you had the UGC objects and you had the CDM overlaid over the rotation curve,
Mm-hmm.
and it had a gray band, right?
Mm-hmm.
And that gray band was due to the variation of the concentration at a given mass.
Yeah, but
And that's sort of what you expect just from dark matter. If it's just dark matter, there's very little variation.
Yeah, that's right. Yeah, so that's just mostly from the assembly history of the halo. Yes. Yeah, I agree. That's a quantification of that. Yeah.
You're saying these effects are 100% of the variation, more or less. the vast majority, because CDM alone explains very little bit, right?
Yeah, that's fair. Yeah, that's fair.
There is something basic, I don't understand. Baryons are there, I mean, it's one thing that we know exists. So when you say I add the baryon, what does it mean? I mean, shouldn't it be a background that is added to all models, whether or not you have
Yeah, I agree.
self-interactions? So shouldn't you have, say, self-interacting dark matter, I mean, baryons plus self-interacting matter?
Sure, maybe I should change the way that I'm talking about it. Yes, I mean, I agree. I mean, but this is like generally the way that people talk about it. You know, they talk about things relative to cold to dark matter only simulations. It's just sort of like the language that is typically used. I totally agree with you. You know, the baryons are there. You know, I think, you know, in some sense, maybe, you know, previously, you know, long ago, why this was motivated is if you look at the matter energy content in the universe, 5% is baryons. The rest, or 85% of the matter in the universe is dark matter. And so, you know, in that framework, you know, initially people were like, oh, well, the baryons shouldn't matter. It should really be the dark matter that matters. But what we're seeing is, you know, galaxy formation, you see galaxies, so yes, you need them. And so, yeah, I mean, maybe we should change the
But
language, but
so if you
depends
have
on who you
both,
talk to.
if you had both effects, you get too much of everything. So
If you add both effects.
I mean, baryons that are there plus interactions.
Yeah, I mean, I think what I am saying is that you can, if you have baryons, you can produce diversity. You can produce compact and diffuse objects. You can produce slowly rotating objects. You can produce, you know, quickly rotating objects. And that doesn't change very much in terms of the diversity of the rotation curves if you go to adding self-interaction, which has a low cross-section, right? Like what happens in the case where you have a very high cross-section? I don't know yet. I don't think anybody really knows in the case where you have a very high cross-section how things will change.
Because that may rule out this.
Yeah. Yeah, I mean, it significantly, you know, changes the predictions that you get if you just consider the self-interactions and you don't consider the baryonic component. Yeah.
So yeah, part of it is that simulating baryons is hard, right?
Yeah.
And so that's part of the answer to the question of why you might try to not consider them at all, I think, right? There's a lot of new parameters you
Yeah,
introduce
yeah.
and then you don't know the right answer for them.
Yeah.
But it sounds like, I mean, yeah, that you're able to get the diversity with CDM plus baryons. Forget SIDM entirely for a second. Why has no one else been able to get from CDM plus baryons? Basically, you just explored a different feedback parameter space that no one else looked at, and so now you've recovered the diversity.
I mean, okay, I mean, in some sense, this diversity of rotation curves is like fairly new. I mean, I guess 2015, so I guess it's been like 9 years. Previously, people were really sort of like after producing cores, right? Like they were really focused on thinking about the core cosmic problem before sort of, you know, Kyle Ullman really realized, oh, it's actually not that you're just producing these more chord objects, you're also producing these things that are more CP rising. So it's kind of like a more, you know, newly emerging problem in some sense. And people's models were really being tuned to produce cores, right? And so their feedback is very strong because they wanted to produce these cores for the core cosmic problem. And so that's one thing. I think that, and then I also think, you know, kind of luck in a way, like we were thinking about these very high, you know, Alison Brooks has really been working, you know, for like the past decade to really produce the most realistic, highest resolution population of dwarf galaxies with, you know, the most realistic prescriptions of galaxy formation that you can get, you know, sort of at where we're at in terms of, you know, our computational power. So in some way, kind of luck, you know. Yeah.
Because it just seems like, oh, is the message at the end of the day, is the title of the paper, there is no problem. Like, is that because you recovered the diversity
I
with
think, yeah,
CDM, right?
I think the title of the paper is resolving diversity in CDM or something like that, yeah. Yeah, I mean, you know, and I think it's not just the diversity though, you know, like these other simulations are also really struggling to produce realistic dwarfs, like point blank, right? Like it's not just the diversity of rotation curves that they're really struggling with, gas mass fractions compared to observations, how big they are, all of these different things that people are seeing, in these other models like Nihao and Fire, right? Like the feedback is just way too strong. So, in some sense, yeah. I mean, I think this is also telling us something about. I think it's something about galaxy formation.
Any last questions? Alright, now let's thank Akaxia again.
I think we should just keep Windsor's notes on the board forever.